Yeah.
I've never seen
But apparently this weekend, players pro players. We should start
All right, so let me share the screen again. And this is what you're listening to. I like to start off with that because music is mathematics. So again, what I hear with my geeky ear when I hear students or usually say I hate math is I hate music. Because it's the same thing, basically the same thing. So somehow you were taught math incorrectly to say that you don't like it or you hate it. And I think the whole teaching system needs to work on that from the elementary school up to our level. So practical mathematics is basically a good metaphor for music. Maybe I have to stop at some of the music today that I listen to when I'm at the gym and playing. I'm not sure what, even when I'm in the, it's good I'm in the pool, I can't hear it because I guess it makes you jumpy if you listen to it. But I just don't get the stuff today because I'm too old to understand it. These are the mathematics for aeronautical engineers. It covers the two technical areas of structures. No, there's no structures in here. So this doesn't cover structures at all. There would be a sheet like this for structures. And this does cover propulsion. You can see there's propulsion here. Let's see if I get my annotation thing going. I love this spotlight if I can get it going right. Yeah, so you can see propulsion here. And then we'll do this the second half of the class. The energy, of course, is in both halves of the class. And then here's the aero part. So we have control and we have propulsion and structures is missing. However, this is the only equation we're going to use in this class because this is the only equation over here for what's called the coefficient of lift that you need to understand to know how and why an airplane flies. Does that make sense? So we're going to take this equation apart. And you can see it's fairly simple, but you need to know what every term in there is in quite a bit of detail. And we're going to do that today because, and remember, this class is front loaded. I'm going to give you probably the most difficult stuff of this first half of the course today. So this is a bad day to miss, a good day to mark with your videos. Or even, I watched my last year video last night to prepare for this. It's quite good, except I'm getting old. You know, I can't listen to myself. It's great before I go to sleep, but man, I go right to sleep after watching it. You guys don't have that problem with me, do you? No, yeah, you will. So this is the equation we're going to take apart today. We're going to start today. So good luck. Good luck with that. Let's see what's next. Okay, that one equation, like I said, I don't want this thing to be blocking everything. I'll keep moving it around if I have to. That one equation depends on a lot of supporting information. And don't forget, a lot of these recorded videos are available on Kansas. You might, or Kansas. You holding it photo? I don't know. They're available on Canvas. So here's a 5-minute video that's pretty cool about the useful formulas that we have. Let's see if it plays. Look at that, it's gonna work.
You can't expect your team to manage work with this. With Monday.com's flexible management system, however.
I gotta remember to pay that guy after class.
This is a very brief introduction to practical mathematics. I define practical mathematics as mathematics that's useful.
You gotta listen to Dr.
Very
Strangelove here for a while.
like flying an airplane. So I'm going to show you some of the conversion constants and formulas that you might want to refer to later in the course. There's two sources primarily. The first source is a file called Useful Formulas Part 1 for AERO 310. You can get this from Canvas, and if you open up the file, you'll see it says formulas for the first half of the course. This is for the AERO course. And there's a whole host of formulas and constants that you might find easy. You can Google a lot of this stuff and get the answers, but this file is particularly suited for what you might use in a discussion or some answer that you might have to find on a quiz or an exam. If I was to look at gravity, acceleration, 32.17 feet per second squared or 9.8 meters per second squared, that's called 1G. Temperature, and if you go through the rest of this file, you see there's the speed of sound, that's a function of temperature, density, and the units of slugs per cubic foot or kilograms per cubic meter. What's a slug anyway? Well, that turns out to be 32.17 pound masses. So 2 bowling balls is a slug, basically. So these are some of the things that are maybe hard to find. Might give you some time that you can find it very quickly here in this set of files. Towards the bottom are ones that I added, particularly from the class lectures on different topics, like Mach number, what's dynamic pressure, what are the formulas for dynamic pressure, and the coefficient of lift. So that's the first source, is this file, which you might want to keep handy, print it out, keep it if you've got it. The second source is a website, which is interesting. It's over here, it's called the Engineering Toolbox, and then it's dynamic pressure dash D. Well, I know you can see it up here at the top. And this is interesting because this takes you to dynamic pressure is the same formula that I used in my except you can actually calculate the dynamic pressure with units. So you can use metric units or SI units or imperial units. In other words, slugs again, feet per second. And if you put a density in here, let's see, I know the density at sea level for our atmosphere is, I think, 0.0023.
Yeah, I did that wrong. See the
slugs
number I
per
put in
cubic
this.
foot, and then hit calculate. And look here at the top, it gives you the dynamic pressure in pounds per square foot. It automatically calculates 1/2 rho v squared for you. So that's kind of cool. That's a nice place, again, as opposed to trying to Google everything. Here's a nice location where it's all concentrated for you. And look on the left-hand column here, the unit converter. You see that? Look like here's centigrades to Fahrenheit on the left, and all you got to do is hit the convert button, and it converts everything. So you can see that what it's done is it's converted 0 degrees centigrade to 32 degrees Fahrenheit, 273 degrees Kelvin, or 492 degrees Rankine. And of course, those are the 4 temperature scales: centigrade, Fahrenheit, Kelvin, and Rankine. So that's kind of cool. And of course, you could change these numbers. You could put Fahrenheit in here and then convert. And now you see 0 degrees Fahrenheit is minus 17.8 degrees centigrade, etc., etc. So that's kind of cool. And look, if I scroll down on the left-hand side, you have conversions for area, volume, weight, velocity. So here's feet per second. So if I want to convert 1 feet per second, let's say I know. Let me just put down. Let's put down 88 feet per second because I know that's about 60 miles an hour. So if I hit the convert button, you can see 88 feet per second, and here it is in meters per second, kilometers per hour, and then here 60 miles per hour, and that's the conversion I remember from my test pilot school days. Is 60 miles an hour is 88 feet per second. So and again, now here you see there's pressure, and so this is a pretty useful site with the conversion factors and kind of a go-to one place. So those are the 2 things I wanted to present to you that might be useful in the first half of the course or on your final exam, is because this will be open book, will be this website or the file, and the file is called Useful Formulas Part 1. And good luck with that. Good luck.
So that file is available on Canvas, and let's see, it should be under week 1, useful formulas part 1. So in the video I just showed you, I think it's right there. That's what we just watched. Yeah. so you can get most of this stuff on Canvas. Okay, so now we get started. Technology. Those three technologies are structures, propulsion, and control. Remember, those are von Karman, the first aerospace engineer, did that. And he said that one of those technologies always limits airplane or spacecraft construction and operation. So Elon Musk has to deal with structures, propulsion, or control on everything he does. Same with Branson at Mojave. No matter how modern it gets, it's always the same three technologies. Actually, there's a fourth. With electronics now, we have what's called avionics. We'll talk about that in week 3. It's part of the guidance and control. So actually, there's almost, you could say, 4 technologies, because the avionics part, the electronics part, is a part of all the other technology, all the other 3. The 4 forces we know are what? The aerodynamic forces are lift and drag. And what causes lift and drag? Angle of attack. The other 2 forces are propulsion and weight. And the propulsion balances drag in equilibrium, and weight balances lift in equilibrium. And here's the formula we're going to see over and over and over again. You can see it behind me on the board. And we're just going to see this like crazy. You'll be sick of this formula by the end of the class today. So at the second hour, I'm going to show you what Khan Academy and the MIT graduate students put out for kids. I watched it years ago, and it was full of errors. So I wrote the Khan Academy and got them to change it. They did a pretty poor job of changing it. So I wrote them again, and I'll tell you that story the second hour today. But it's kind of an interesting thing, of how this developed and how careful you have to be when you start getting information off the internet. And one thing I know about myself, my family, and I have 2 college students living with me at home. One goes here, one goes to Cuesta. My granddaughter is 7, and they just live with Google and electronics. So that's their new Bible. Then I have some errors from the flight instructor. I'm going to postpone this till next week because we have a lot to cover today. So I'm not going to show you that lesson from the flight instructor of how this stuff applies to an airplane. We might remember this from yesterday. So I'm going to get this thing out of the way. So this was Denzel, and we were asking if he could fly this airplane and roll it. And I'm going to stop it as it goes along so we can follow. You'll see the 4 forces acting on this airplane. And what I stopped it right here is what's called the altimeter. The altimeter is a crucial instrument, and we're going to go into in some depth because we live in a pressure bubble. We're actually fish. We're like fish in a bowl, except we don't know it because the bowl is so big we think we're free. But we live in the atmosphere, and we're under pressure in the atmosphere. You don't really realize it until you go into the water and dive down about 8 or 10 feet, feel it in your ears. But that's what happens now, right now. If you go up very high, your ears would pop. If you've been in an airplane go down, your ears, you have to Valsalva, right? You just try to get it out because we're living in a fishbowl called the atmosphere. The altimeter measures the pressure in that atmosphere, and it tells the pilots how high they are in that atmosphere, which is a mathematical atmosphere. It's all math, right? So we'll go into that, but I wanted to just point out, he does show this altimeter that I'm pretty sure anyone watching the movie had no clue what they were looking at. Got a jam stabilizer or something. Okay, he just said we have a jam stabilizer. I love Denzel because he's talking like a pilot, right? What is the stabilizer? Stabilizer is the rear horizontal stabilizer. It's this piece right here. The rear horizontal stabilizer is what makes the airplane pitch up and pitch down. His is jammed. It's jammed. So it only will let him go down. It'll only let him rotate the horizontal stabilizer such that the nose points into the ground. That's the problem that he's got. There is the altimeter, and it's unwinding down. He's at 8,440 feet in the atmospheric bubble. I don't know where he got that co-pilot. I want to dump that guy right away, but Denzel keeps his head, which is kind of cool.
Say, I want you to retract the flaps.
Okay, he wants you to retract the flaps. What's that? You got this when you watch the movie, right? Every moviegoer would understand totally what Denzel was saying, right? So the flaps are the part of the wing over here, the trailing edge. They go down to change the camber to make the wing look like a whale. It makes the cross section of the wing look like a whale when the flaps go down. And he said he wants you to retract the flaps. In other words, he's got the flaps down now for landing, but the airplane is pitching down, so he wants them to retract the flaps.
Track the gear, trim us nose down, okay?
Oh, and he just said he wants us to trim us nose down. So in the cockpit, he has a button on his wheel that he can push. When he pushes that button, electric and hydraulic signals go back to the stabilizer and move it in such a way to push the nose down. Now, they already can only go nose down, and he's telling the co-pilot to trim it so it goes nose down. So he wants to move the stabilizer so it goes nose down, even though the airplane, that's the only way he can go. And of course, the co-pilot's clueless because he hasn't had my class. If he had this class, he would be a lot calmer, right? He would know what Denzel's doing.
Trim down, what are you gonna do? When I tell you I want you to push these forward, full throttle.
He just said he's going to push the throttles forward. So not only is he going to trim nose down into the ground, he's going to go faster. And May just doesn't want to live much longer in a state of fear.
Okay, when I tell you, sir, what are we doing? Why would I trim down? We're gonna roll it, okay? What do you mean roll it? Gotta do something to stop this guy. Here we go.
Okay, he said we're going to roll it, right? Now you got an idea of kind of what he's going to do. He's going to trim it nose down. The airplane only wants to go nose down. He can only control it nose down, but he's going to roll the airplane. And when he trims nose down, he's going to put an angle of attack, a negative angle of attack on the wings. And he said now he'll be able to fly. Okay? So now you kind of got, it's just reminding you what's in the movie. And it's pretty accurate, that part of it, what he's saying to do.
I got control. I have flaps. Speed brakes.
He just called for the speed brakes. Now what's that? Actually, his airplane doesn't have speed brakes. They're called spoilers. But speed brakes are flaps in the center of the wing, like where that star's at, and they're flaps that come up to slow you down. So if you're flying a glider, you always fly with the speed brakes half out, because then it's like a throttle. So if you want to go faster in a glider, you retract the speed brakes. It's like adding power, or you pull more speed brakes out. But they're actually in his airplane. They're called spoilers. Speed brakes aren't on small jet trainers like this. They are on fighter aircraft. You have speed brakes, and of course, all big airplanes have spoilers. They deploy when you land, so that you can slow down and stop in the available runway. That's what he just called to put the speed brakes out, or spoilers out. And now you can see the difference between flying a loop, as we talked about yesterday, when you keep a positive angle of attack, or a barrel roll, where you keep a positive angle of attack, nothing would happen to those people in the back. But he's actually he's going to go negative angle of attack, right? And that means that there's going to be chaos in the cockpit. Stuff's going to fly all over the place, and the people will fly out of their seats and hurt themselves on the ceiling. That's it. Oh, that's so cool. So that's what we're going to talk about today. We're going to talk about Denzel. And of course, he didn't mention anything about angle of attack. But what's missing, this is just, let's just take you to the video that we just saw. What's missing, of course, is angle of attack. So the angle of attack, or the coefficient of lift, angle of attack and coefficient of lift are only off by a constant. They're only off by the lift curve slope. So they're basically the same thing. If I increase the angle of attack, I'm increasing the coefficient of lift. Decrease the angle of attack, decreasing the coefficient of lift. They're tied together linearly until the stall. Once the airplane stalls, game's over, airplane stops flying and it falls. The question here with Denzel is, can he fly upside down like that with a negative angle of attack without stalling? That's the question. That's what we're going to look at today. And if you understand the answer, you'll be doing well to understand the fundamental principles of this course, the first half of the course. This is just a review of what we did last class. Remember, the relative wind is the opposite of the way the airplane is going this way. It could be going this way, it could be going this way, descending. If the relative wind is the way the airplane is going, the angle between the relative wind and the chord line of the wing is called angle of attack. And if that angle is positive, the pilot and any passengers will always feel pressure down in their seat, just like you're feeling right now. Right now, you feel 1 G, 1 times your own weight, right here. If we would accelerate the room rapidly up, like an elevator, you'd feel 2 Gs, maybe you'd feel twice your weight. So the number of Gs is the number of times your weight. And if you increase the angle of attack fairly rapidly, you'll increase the number of Gs, and of course you'll climb. Or if you decrease the number of Gs, you'll descend. And your relative wind will follow that command. As we did yesterday, dynamic pressure is important. It's called Q. Some people call it Q bar. So, but Q in aerospace is dynamic pressure. It's what you feel if you put your hand out the window in a car, or a sailboat if you're sailing with wind in your face. That's dynamic pressure. And that's 1/2 times the density. The density is often called rho, Greek letter rho. And then the velocity through the air squared. It's airspeed squared. It's not ground speed, it's airspeed. So your Q depends only on your velocity through the air. I talked last class about having a balloon. You let the balloon up and it takes off 30 miles an hour towards the airport. It has no airspeed. You see that? It only has ground speed. There's no airspeed because it's moving with the wind. If I held the balloon in the 30-mile-an-hour wind, then it would have airspeed, even though it's not moving. So you got the difference there. You get the important difference of how Q only depends on the motion through the air. Okay. So we call true airspeed TAS, true airspeed, or you might see VT. Let's shorten it to VT. If you're not, there's lots of velocities. We'll see next week. There's lots of velocities. They're all important. So we have to remember what true airspeed and density determine the dynamic pressure. There's the formula at the bottom. Q is 1/2 rho V true airspeed squared. Right. At sea level, rho is a constant, 0.00238. So I put the wrong number in as a demo. I like the video so much I keep it. It's the only mistake I ever made. So rho at sea level is 1/2 is 0.00238 slugs per cubic foot, and the velocity then is in feet per second. And that'll give you then pounds per square foot, something that we can understand what that is for Q. Pressure in your face. Pressure in your face. This we talked about last class also. If you have a symmetric wing, the symmetric wing would be like the tail here. It doesn't care whether it's upside down or right side up. It doesn't know anything about its orientation. It's symmetric. And notice there is no lift. Those lines generate how the air is flowing. There is no lift. If I put camber, if I make the airfoil look like Moby Dick, if I make it look like a whale, right? Then I have this wing, this kind of wing. I take the cross section of that, and it will have lift at 0 angle of attack. All airliners have lift at 0 angle of attack. They look just like this. Okay, and then the wing throws the air down, and that puts an upward force on the wing. And as you increase angle of attack, then you will get. So if I were doing a plot, the angle of attack versus C sub L would be off only by a constant, by what's called the slope. And over here, a symmetric wing at 0 angle of attack would have 0 lift. 0, 0. If I have a cambered wing, what would you think happened? If I had a cambered wing, well then at 0 angle of attack, I would have some lift. You see that? So the slope would stay the same. The slope would stay the same, but I would have lift at 0 angle of attack. So the plot for a cambered wing would look like this, or a symmetric wing would like, and the stall would probably be higher C sub L for a cambered wing, and then a more abrupt break, and probably at a lower angle of attack as well. That's angle of attack. So that's the mathematics that we're going to repeat over and over again. And I guess the important thing is to realize that wing shape is what aero people call camber. So when you move the flaps, or what's called the slats are things on the front end of the wing that go forward. If you move either one of those, you change the camber of the wing, you're going to change that curve. Okay. That's pretty much what changing the shape reads. And the coefficient of lift varies in a linear fashion with angle of attack. What does linear fashion mean? It means that. It's a linear line. That slope is always about the same. That slope is about 0.05. So in other words, at 2, the angle of attack is normally around 20 for typical airplane. A C sub L of 1 gives you 10 degrees. C sub L of 2, if you can get there, would give you 20 degrees. Yeah, go ahead.
Is that linearity a property of all wings, or are
Pretty
wings
much
designed to be that way?
Yeah, the question is this linearity a property of all wings? Yes, it is. It's proper. It's a might fly all over the place, and the slope is relatively constant no matter what kind of wing. At least one of the things von Karman discovered way back when. Good question. Thank you. So highly cambered wing has a large coefficient of lift, about 1.5 or 2, and then that actually I should have 15 degrees and 20 degrees there to go with the example I gave you, rule of thumb on the slope. And the intensity of air impacts the wing. The intensity of the air in the space is called Q, dynamic pressure. And Q has a formula, 1/2 density to airspeed squared. If you're at sea level, the density has a constant value, and the true airspeed becomes what's called equivalent airspeed. It's a pressure airspeed at sea level. And we'll talk about that more next week. I just throw that out there because we're going to see there's lots of different airspeeds, and Q can be defined relative to sea level or relative to the altitude that you're at. Okay, here's an example of using the engineering toolbox to figure out what your dynamic pressure is. So let's see if he hasn't lost his way.
In this example, we're going to try to find the dynamic pressure when the velocity of an aircraft is 100 knots, it's nautical miles per hour, and we want the answer in pounds per square foot because we have an idea of what that is physically. So in order to do that, we will use the formula. Dynamic pressure is 1/2 density rho times true airspeed squared, v squared, where the airspeed is 100 knots. Now, since we use the density for feet in the units of SI or the imperial units, we're going to have to use the slugs that are defined, or the density that's defined as slugs per cubic foot. And don't forget, a slug is about a little over 32 pound masses, or about 2 bowling balls. And in slugs per square feet, the density at sea level for the atmosphere is 0.002377, or 0.00238 is a good answer. That's what we're going to use. So that's the first thing that we have to look up, is the density in sea level for our formula. And the second one we're going to have to use is to convert our knots using the engineering toolbox into feet per second. So we'll put 100 knots in the engineering toolbox, then hit the convert button. And then this box will pop up, and we see that 100 knots is the same thing as 169 feet per second. That's the units we want to get pounds per square foot. So we're going to use 169, and we'll use the slugs that we got from the constant book. So when we do that, using the dynamic pressure calculator for imperial units, which is slugs and feet per second. We'll put, for our density at sea level, we'll put 00238. And the velocity we got for 100 knots is 169 feet per second. And then up here we can see that the dynamic pressure in pounds per square foot is 34. So that's how you would use this constants, the engineering toolbox, with various constants and various different formulas to make sure you keep in the same set of consistent units by using either the formula PDF file and or the engineering toolbox with conversions. And that's it. Good luck.
So, so you might say, well, I can do that with my calculator. I got a calculator on my cell phone. I can do that on my calculator. Okay, so what's going to happen typically is you're going to do it and you won't get the right answer, or you'll get different answers from the people in your group. And the reason almost invariably won't be because you're doing it wrong. It's because you're mixing units. You might put knots in there instead of converting it to feet per second. So that's why I recommend first couple times, if you're working these type of problems, to avoid spending a lot of time trying to troubleshoot, use the engineering toolbox. It forces you to pick your units. You see what I'm saying? You have to pick the right units when you use the engineering toolbox, where your calculator doesn't care what numbers you throw in there. So let me throw that out. If you have no problem using the calculator, convert it, that's fine. Then do it that way. Whatever works for you. So it's just a reminder, and all this stuff is on Canvas. All it's on Canvas, and you can look at it.
In this example,
this kind of a review. Remember that wing shape is the same thing as camber, and that wing shape creates a difference in pressure between the top and the bottom of the wing. If it has camber, it'll generate lift even at zero angle of attack. Now, I'm pretty sure this is what NASA had in mind when put that drawing on that I put on last class. That's what it had in mind. There's no way you can generate enough lift for a practical airplane to fly at zero angle of attack. You have to be flying at 600 miles an hour to take off. So that was my objection to that. That it's just the beginning, and there's lots of mathematics that goes into this Bernoulli's principle that we're not going to go into. For our purposes, angle of attack generates it, and a cambered airfoil increases the lift at a given angle of attack. And this formula, the first variation, is very interesting. The first variation of this formula replaces lift with the number of G's times the weight. Again, right now, your lift is your weight, so the number of G's, your NZ, is 1. NZ stands for normal acceleration. That means you're actually feeling as if you're accelerating at 32.17 feet per second squared, or 9.8 meter per second squared. That's what we're feeling. In other words, you wouldn't know if you're sitting here or if we're accelerating 32 feet per second squared. You wouldn't know. You're just experiencing 1 G. So if we accelerated the room, then NZ might go to 2. That means that you'll feel twice your weight. It's something I don't need to do. But anyway, you'd feel twice your weight, and NZ would go to 2. For an airplane can pull, as increasing an angle of attack at high speed, it can pull up to a maximum of NZ max. Airplane like this, T-37, can pull about 5 Gs max. Airplane like this, T-38, my favorite airplane. I got about 800 hours of this, not this model, but this airplane. They just retired it, by the way. So I guess there's a message for me there too, isn't there? Air Force just retired this airplane. Beautiful airplane. This airplane can pull 9 Gs. 9 Gs. So the pilot typically pulls 6 in training. That means you're 6 times your own weight. Just think of that. So if you're 150 pounds, imagine what 9 Gs is. You're over 1,000 pounds. So it can get very physically demanding. Amazingly, not amazingly, women will get after me. Women can pull more Gs than men. We know that from testing that women can pull more sustained Gs than men. So, I mean, and women are now becoming fighter pilots because of that. So that's an interesting thing that came out that people weren't expecting. I think they were expecting it to be equal, but they're not. And my guess is it's because the aorta of the average man is bigger than the aorta going up to the brain of the average woman. So it's harder to constrict the aorta in the man. He tends to black out sooner, especially if it's a marathon runner. You put a marathon runner in an airplane in high G, he's really working. He's really working to keep his consciousness because he's got these huge blood vessels going through his brain and the blood's trying to pull it down from his brain. So what we're going to do now is start playing with this equation to give it a physical insight of what's going on. The first thing I'm going to do is solve for what's called the coefficient of lift. So let's look at that. What I did is I pulled the area over to the left-hand side. That's not hard. Then I pulled Q over to the left-hand side. I just kind of solved for C sub L, and I put it in this form. Now, why would I put it in this form? Well, look carefully. At the top, the lift over wing area is pressure. It's what's the pressure that's pushing the airplane up? And what's on the bottom? The pressure in your face. So you could look at this equation is how efficiently or how effectively is my airplane converting in the face pressure to lifting pressure? And you would expect that the maximum you could do that is 1. You would expect I can't create any more lift pressure than dynamic pressure. This hampered the sailing industry for centuries, right? I mean, for centuries, people thought you could only sail downwind with the speed of the wind, right? Now we know, no, the sail is just like a wing. It generates lift. And when the lift, if the lifting pressure is greater than that can be greater than the dynamic pressure, you can have lifts of 1.5, which is amazing. You're generating more lift than you're feeling. You're taking the energy coming in and converting that energy into more lift pressure than the energy pressure coming in. So you can sail faster than the wind. That's only been known for, I don't know, 50, 60 years. Probably started to turn of the last century before people figured out I could sail into the wind faster than the wind is blowing. That's because of this equation. So this lift over SW is called wing loading. It's the pressure acting upward on the lift. And of course, G's are involved in it. It's also related to the number of G's. If I pull too much pressure at NZ max, I will bend the wing or break the wing. And that's what you can see from that formula. So typically C sub L has a value of 1 when you're generating enough lift to match the dynamic pressure coming in. You'll have a C sub L of 1, and that's going to be an angle of attack of around 10 degrees because C sub L and angle of attack are tied together. The same thing. This formula works for sailboats just as well as it does for airplanes. You can see that this is a pure number then. It has no units because there's pressure on the top, pressure on the bottom. They cancel, so C sub L is a pure number. But the number has an amazing physical meaning, doesn't it? I mean, that number is 2. That number of 2 means I can generate twice as much lift pressure as the dynamic pressure coming in. And that's why you have flaps and slats and all kinds of things that change the camber of the wing. So you can generate high C sub Ls when you need to land or take off, especially at high weight. And of course, if I'm looking at C sub L, I'm looking at angle of attack, right? They're only off by the slip, by the lift curve slope. So that formula is right up here. The lift coefficient equals a lift curve slope, often called CL alpha, and the angle of attack gets the Greek letter alpha. Here's a longitudinal aircraft. You can see it's in equilibrium and level flight. So the velocity vector is level. The angle of attack is the angle between the velocity vector and the axis, longitudinal axis of the chord line. That's the angle of attack. And then here's your dynamic pressure that's converted into lift pressure. And then in level flight, the weight, mass times gravity, balances the lift that's generated to counter weight. And the lift is a function of dynamic pressure, and dynamic pressure is a function of density and airspeed. That's a lot. I mean, it's just one little simple formula, but do you have to know everything that I'm just saying? All these? Yes. Otherwise, the math has no meaning. If it's a bunch of variables for you, It's just it's just a bunch of variables. What we want to do is we want to put physical meaning on each of those terms so we can understand what happened. And when we start looking at the aircraft accidents next week, we'll see how a fundamental misunderstanding of some of these terms kills people, right? Even with seasoned pilots. So lift equals weight in equilibrium level flight, perpendicular to the relative wind. It's generated by the coefficient of lift or angle of attack, and that depends on the camber of the wing and the angle of attack that it's at. Here are some typical slopes from NASA. These NACA are old terminology for NASA wings. And you can see the symmetrical wing. Look at this. Symmetrical wing has 0 angle of attack at 0 lift. Because the symmetrical wing, like the tail here, doesn't care whether it's right side up or upside down. It's the same. The cambered wing, on the other hand, look here. At 0 angle of attack for a cambered wing, that'd be like an airplane like this. Look at this. We're generating lift. All right? We're converting 3/10 of the dynamic pressure into lift at 0 angle of attack. Now think about this. If in Denzel's case, right? The lift is helping him now flying in level flight. What if he rotates upside down? That lift, that 3/10 is not pulling. See, he's going to have to generate negative angle of attack to counter this loss when that airplane goes upside down. So you can see he's going to increase the negative angle of attack. He's going to have to increase it significantly just to keep level flight because his wing is not symmetrical. Question?
Are the coefficient of lift and the angle of attack the same thing?
The coefficient of lift and the angle of attack the same thing. Practically speaking, at low angle of attack and low C-sub-L, they only differ by a constant. Practically speaking, they differ by a slope. The slope is like 0.05. So 0.05 times your angle of attack gives you your C-sub-L normally. Once you hit stall, all bets are off. Okay. Once you hit stall, all bets are off. So if you're not in level flight, if I start maneuvering that drone, if I start maneuvering it, then my lift is going to be a function of weight. The normal acceleration or the number of G's can increase, and I will increase up to the maximum capability of the aircraft. So here's some ways that you can change. So here on the left, over here, these are flaps. All these guys are flaps, different kind of flaps. And basically the flap, again, is this part, the tailing part of the wing that you move down with a lever in the cockpit. And you can see the effect on the lift curve slope over here. Here's a no flap case. If I start dropping different kinds of flaps, notice I get more lift, but look at the slopes. You see how the slopes are pretty much stay the same? That slope pretty much stays the same. It's just that I get more lift when I add these flaps, and the angle of attack at stall. Look how abrupt that is. See, this one is nice and smooth. The stall angle of attack here, actually what happens to this airplane, it starts to shudder, or stall this one many times. It just shudders to the sky. If you try to stall this one with the cambered wing, as soon as you hit the angle of attack, it falls. It falls right away. So, and that's kind of what the effect of flaps does on your aircraft. You also could have slats, wing slats, and this is the front of the wing. Yeah, this airplane doesn't have slats. But if this airplane had slats, it would be over here on the front of the wing, the front, and they kind of droop down. And notice in this case, the slope stays the same, but the curve is not shifting. It's just the angle of attack, the stall gets bigger, and the lift gets higher. Maximum angle of attack increases, and the max lift increases with slats. If you have both slats and flaps, then you have both effects occurring at the same time, but the slope doesn't change a whole lot. It's just kind of interesting for this curve. All right, so let's look at this. There's a wing that Denzel's flying. All big airplanes have cambered wings. So if a cambered wing generates lift at 0 angle of attack, and if he rolls it upside down, now he's got this negative lift he has that's generating. So he has to put negative angle of attack on it just to get it level. So he's lost some angle of attack. He's used some of that residual angle of attack just to maintain this level flight. So the answer appears to be no, you're going to have trouble, Denzel, flying upside down. So the lift curve slope is going to be for this curve. And if we want to see what that looks like upside down, then we have to rotate it, this vertical distance, we have to go rotate it down. The symmetrical curve would stay the same. We put this cambered, this 0.3, we have to go down here to 0.3. We move this curve down to minus 0.3. Then we change the sign. This would be plus to minus angle of attack. If we want to look at the, we have to generate this 0.3 for a cambered wing when it's upside down. So if I were to do that, the curve would look like this. In other words, so here at 0 angle of attack, I'm generating negative lift now instead of positive lift. That's a positive angle of attack. So to get back to 0 over here, to get back to 0 lift, I have to have -4 angle of attack. So when I roll the airplane upside down, I'm gonna start falling. Denzel is falling. So he has to push it. Again, that's the only control he had. He has to push it forward to -4 degrees angle of attack just to get to 0, right? Now, suppose he was at 0.6 before. Suppose he was flying over here at 0.6, and he's now upside down. Well, he has to go to 0.6. He has to go, holy cow, he has to go -11. So he has not only to go -4, he's got to go minus, so he's got to fly like this, take a huge bite. And what happens if this airplane was at, say, 0.9? It's he was flying at 0.9, which is not uncommon for an airplane on landing approach. He's at 0.9. I rose upside down. Whoops, he can't make it. You see that? Because he's used up the angle. He's used up the angle of attack. And so the airplane will stall. It'll stall before it gets there. So what can we conclude? Well, it's Denzel. He's going to do it, right? So what kind of airplane did he have? He had a light passenger load, because the heavier the airplane is, the higher up, more lift you need. So he didn't need a lot of lift. He was out of gas. It's okay. He's at the end of this flight. Maybe the people weren't carrying much luggage. So he has a very light airplane, right? A very light airplane, and he rolled it very fast, because normally when you roll a big airplane is going to want to roll into the ground. So he had to roll it very fast. That's what he's saying. Push the throttle forward, flaps up, and he's going to roll it maximum turn, roll this thing. See if he can roll it fast enough. Now, I've done a barrel roll in a big airplane, right? I don't know if you could do it close to the ground, but it's Denzel. So let's say you can do it. So we can say that it's possible if the airplane had huge control surfaces, it's flying fast enough to let him roll quickly, and it was very light. And that's what the equation says. It's possible, but I wouldn't do it every flight, just to practice, right? Remember this guy? Now maybe what this guy did made some sense. He had a monoplane symmetric wing, right? He put a landing gear on top of his wing. Put a landing gear on top of his wing, because Blériot, the guy that built the first monoplane, flew across the English Channel. That had too much camber. So Gustav Tweer fixed it, put the gear on top of the wing, and now they have airplanes like this do it every year at Oshkosh, Wisconsin, in the air show. Well, that's my granddaughter.
Hi, my name's Hayden. I'm 6. I'm the granddaughter of your teacher, and I'm a group in my school, and I hope you make a group and make friends, please. And
So you'll probably see more of her. Let's see if I can. Here. Okay, so this is the video. This is the video from MIT and Khan Academy, and I don't have the original to show you, because I usually ask the class to find the mistakes that are on it after the first hour. But you won't be able to do that because they finally took it off. They took it off. I've been writing them so many letters. I think they finally took it off. So you're going to see the corrected Khan Academy video. I love these guys. These are graduate students at MIT, and they did a great job. They really meant well. But what was missing was some mentoring and some feedback on to correct some what I don't consider minor mistakes, but to correct some key mistakes that they made. The presentation was very good. It suffers from what I would say suffers in your generation, is that people want to sell their videos. They want to get the likes. They want to get the money from YouTube. And they say, well, I'll just talk about GPS. I'll just talk about this. I'll talk about the RS-71. Well, that's fine, as long as you check what you've written with an RS-71 engineer or pilot or someone who knows what they're doing before you publish it. Because there's so much stuff out there that's misleading. And again, I'm showing you things from NASA. I'm showing you things here from MIT, Khan Academy. And I don't know if people like me correct it when they see it or not. I really give a lot of credit to the Khan Academy because they did correct it twice. Now they finally pulled it off. Because I guess they didn't want any more letters from me. So here's the corrected video. I think you'll enjoy it. But I have to watch an ad first.
So this is an airplane here. Flown in one, or maybe you've just seen them fly. But even if you've seen them or been in one, do you know how they work? Is it magic?
Wingardium Leviosa.
Are there invisible fairies that hold the plane aloft?
All right, men, we've got a busy morning and lots of flights to carry.
Or is it science? Well, you can guess that the answer is indeed science.
That's ridiculous.
What?
So to discuss how an airplane flies, we first have to talk about the forces on an airplane, which push it around in all sorts of different directions. The first force acts on all of these vehicles. Really, it acts on everything. It's the weight force, which points down towards the center of Earth. Weight is equal to the mass of the airplane, m right here, times the acceleration due to gravity. Here on Earth, g is equal to 9.81 meters per second squared. Now, that's only for Earth. The acceleration due to gravity really depends on the mass of the planet that you're on. The larger the planet, the higher the gravity. So 9.81 meters per second squared here on Earth. The moon, however, it's smaller than Earth, so the acceleration due to gravity is only 1/6 that on Earth, 1.6 meters per second squared. This is why astronauts can bounce high on the moon, but not on Earth.
This isn't nearly as much fun.
Obviously, there has to be another force opposing the weight and pushing the airplane up. This force is called lift. Lift operates perpendicular to the airplane's wings, which are...
That is error number 1, as lift acts perpendicular to the flow direction or the relative wind.
Sorry.
Now, if these are only two forces, our aircraft will be able to go up and down, but it won't go anywhere. So we have to have a force that pushes the airplane forward, and this is called thrust. All vehicles have thrust, otherwise they wouldn't go anywhere like our airplane. On an aircraft, this thrust is produced by engines. There are two main types of engines. We have propellers, like this little guy right here, and jet engines, like our first model. Whatever the type of engines, they all work by the same principle. So if we draw a little side view of an engine here, the engines accelerate air out the back, this direction, and by Newton's third law, there's an equal and opposite reaction, and that's the thrust force, pushing the aircraft forward. This is really the same thing that happens when you blow up a balloon and you let it go. The air comes out the back and the balloon moves forward. We have a force that opposes the thrust. It's called drag. It points opposite the direction of flight.
Note the direction of flight is along the relative wind or along the flow vector.
The major type of drag is pressure drag, which is the force caused by the air smacking into the airplane.
He is neglecting a major cause of drag called induced drag, which comes from the generation of lift itself. This is a serious error.
Feel the pressure drag when you stick your hand out the window of a moving car. Honey, your hand, please. When your hand is horizontal, it's aerodynamic, and you really don't feel a lot of drag. But if you slowly turn your hand vertical, you can really feel the drag increasing.
That's cute. That's not great.
So these are our four forces on the airplane.
Let's look at the equation for the magnitude of lift per unit wing area. We'll call that L.
L equals 1/2 times rho times CL times V squared. It's that simple.
Here is another serious error. He misses the wing area, S sub W, in the equation, which is a critical mistake.
Okay. I'll tell you what each of these things mean. So rho, it's not a P, it's the Greek letter rho. Rho is the density of the air, which is a measure of the number of air molecules in a certain volume. Density of the air varies with altitude and temperature. So as you go higher up, the air is thinner, and so the density is lower. If we want to simplify things, we generally use the standard density, which is 1.2754 kilograms per meters cubed. V here is the speed of the aircraft, or how fast it's traveling. And CL is something called the coefficient of lift. It's a number that gives us some information about the shape of the aircraft's wings. These things right here. The coefficient of lift changes with the angle of attack.
Angle of what?
Aircraft can pitch up and down. And even if they're pitched up, they're still traveling in a horizontal direction like that. Now, the angle formed here by the horizontal direction of travel and the direction of the aircraft's nose is called the angle of attack. And we denote that with the Greek letter alpha. So we can make a little plot here of that. We're going to put coefficient of lift up on the y-axis and the angle of attack down on the x-axis. So as the airplane starts to pitch up, if I can get a little hand here, thank you. As the aircraft starts to pitch up, the coefficient of lift increases. This is a good thing because we have more lift. As we continue to increase, we eventually reach a point where we keep pitching up, but the lift starts decreasing. This is something called stall, and it's not a good thing. So we generally avoid trying to pitching up this much.
There's a similar equation for the drag per unit wing area, D. D equals 1/2 rho,
not CL, that really wouldn't make any sense, CD. As you can guess, it's the coefficient of drag times the velocity squared.
Once again, he makes the serious error of eliminating the frontal wing area. That is the wing area that's perpendicular to the relative wind, or to the flow. It's totally missing from this equation.
The coefficient of drag it's another number that tells us something about the wings, and it also varies with the angle of attack. So as the angle of attack increases, thank you, the coefficient of drag increases as well. Thank you very much. This is because as the aircraft is pitching up, there is more wing area perpendicular to the flow. Now,
Okay, so this is kind of important because of the mistake that was made earlier with the hand out the window. Okay, it's easy to confuse drag with pressure, the pressure that you're feeling. And the pressure is Q. That's what's coming in to the front. Now the frontal area of the aircraft, this area, whatever that area is the area that causes drag. So you can see this drag that's sloping up over here, a drag that's sloping up on the right, that's induced drag. That comes from the angle of attack. Remember last class, I said the ag solution for this is what? The air is taken and thrown down. It's thrown down and it pushes the wing up. That throwing down creates a vortex. The vortex trails off the wing like this. It's turbulent. It's like the rock in the river, like turbulence of the Grand Canyon, the Colorado River, right? That's induced drag. That is what's pulling the airplane back. That's what's making that curve at the lower right go up with velocity. It isn't the pressure Q. The pressure Q exists at zero angle of attack, right? But then as you increase the angle of attack itself, because the air is being thrown down, creates this turbulence, and that creates the excessive drag that he shows here.
In this final error, he has once again eliminated the frontal area and is confusing drag with the coefficient of drag. The drag equation must have the frontal area in it, which is missing. The coefficient of drag varies with the angle of attack as well, but it is totally missing from his equations, and so his examples are not correct.
this reminds me of something that we talked about earlier. Exactly. This is very similar to whenever you hold your hand out the window.
Yes, and it exists. This is exactly the term that is missing from his equation, the frontal drag area that increases, just like holding your hand out the window of a car, but it's missing from his equation.
Window of a car. And so that's pretty much everything you need to know about how an aircraft flies. So the next time you're on an airplane or you just see one, you can really know exactly what it is that's keeping it up in the air. Nope. No, it's not them either. There you go. Now you got it.
I contacted the Khan Academy about these errors, and they fixed them by saying at the start of the lift and drag sequences, lift per unit area and drag per unit area. You can notice the change in the voice file when that occurs. But still, there's, I think, serious misconceptions that are conveyed by this video, and I hope that that you have them straight in your own mind. Thank you.
Okay, so what they did when my first correction, the first correction, they redefined lift. They redefined. If you go back and listen to it, you hear lift. The voice changes because they put it in as a overlay. Lift per unit area, drag per unit area. So they took this term here and they put it in with lift, right? Like a kid's gonna catch that. So then I contacted them about the confusion between Q and drag, which is a subtle difference. I think they should have avoided it entirely. And then they took it down. So I don't think you can get this anymore. I think they figured I wasn't being. I love these guys. They would have all gotten an A for me, 100 for the presentation. But what it needed was a little critique from someone at MIT. All they had to do is go to one of the professors. The guys would give them some time. I don't know why they wouldn't, and say, "Hey, look at this, and what do you think of it?" And I'm sure any of the professors there would have corrected. But one of the reasons I keep highlighting this is to once again get across what I see your generation, and now my own family, even the older people, my wife, certainly my daughter and my kids, they Google everything. Google's the Bible, or replace the Bible, right? Whatever you want to know, I mean, I just Google it, and that's the answer. Yeah. My grandson loves to Google and correct. It's easy for him to do because I screw up so often when I'm talking now. I say wrong things, say missing. Because that's not right, Grandpa, you know, because it's something you Google. So I realize it's there, but if you're working for someone someday, then I would suggest that you use multiple inputs and try to look at the mass controversy going on now with I don't know who to believe. I mean, I get contradictory information from almost every source, no matter how scientific the source claims to be. One doctor says this, another one says this, another. So how you get through this cacophony of information? Well, you're kind of on your own. And the first thing to realize is that the way I'm thinking right now may be wrong. It may be an error. Let me look. Let me ask. Let me find out. So as opposed to automatically taking sides on something and only listening by confirmation bias to the things that you've already made your mind about, which causes only controversy. So I love these guys. They would have done great. And I hope you see them, what I was trying to get across with the pitch. Okay, so let's look at how the airplane is controlled. It's got 3 axes. It's got a pitch axis. The pitch axis would be this one, right? And that's controlled by what we call the horizontal stabilizer. Horizontal stabilizer is this piece. It can come in one piece, like P-38. It just has a horizontal stabilizer. Or the horizontal stabilizer can be divided into 2 pieces, a elevator and a horizontal stabilizer. Okay, so if it has an elevator, then that's the control surface that the pilot moves in the cockpit. He moves the elevator. The control surface in a big airplane that controls what's called the trim. You heard Denzel talking about the trim. That trim controls the whole orientation of the whole stabilizer. So it's normally an electronic hydraulic thing that moves the stabilizer relatively slowly. And we'll see next week or the week after how a malfunction of that caused those 737 MAX jets to kill over 500 people. Right? I mean, a horrible tragedy. Boeing still hasn't recovered. They may never recover from those 2 accidents. But that was a trim malfunction. So that trim moved the entire horizontal stabilizer. The pilot controls the elevator in the back. A very small airplane, a tiny airplane that you go fly, here a Cessna 150 or something, it would have what's called a trim tab. And a tab is a tiny little piece of surface on the elevator And when you move the trim tab, you got a button in the cockpit, or you got a wheel that you can turn. It moves that tab, geometrically moves it, physically moves it. That creates an air load that bends the elevator. So what it does is it relieves forces. If I pull back and I'm holding force, I move the trim tab in the small airplane, it moves the elevator with air forces, and then I can let go of the stick. That's called trimming the airplane. In a big airplane or a fighter airplane like this, that's done with springs and balances, right? Some with springs and balances, and it's called the force field in the cockpit. So I get some force when I move the control yoke in the cockpit, then I can trim it off. And different things happen in the big airplane. That's called trim. So the horizontal stabilizer is a key thing in almost all the accidents we're going to talk about. All the accidents, and a lot of misinformation about how that works. The rudder is the vertical. The vertical stabilizer has a thing on it called the rudder, and the rudder acts like the elevator. It moves back and forth. The rudder, the vertical stabilizer does not move. Only the rudder moves. But it can have a trim tab also. A little trim tab that you move in the cockpit, a little button, and then you'll then put an air load on it. And then there's, of course, the ailerons. The ailerons control the roll. So we have the pitch is controlled by elevator and trim. And then the rudder controls either your feet. Your feet move the aircraft right and left, right? And then the rotating the stick, like you're steering wheel in your car, or it's the stick, you move the stick off to the left. That will move these ailerons in opposite directions, creating a torque that rolls the aircraft. So those three things, pitch, roll, and the rudder, are what makes the aircraft work. Okay, so let's look at this equation. What's maneuvering flight? What I was talking about earlier is equilibrium level flight. So up to now, we've had this airplane flying level in equilibrium flight, 1G. But what if I add power and pull back on the stick? I'll pull more than 1G. Or I could go into a turn. I could go into a level turn and pull more G's to stay level. Then I lose a lot of lift when I roll. So I could go into a turn and pull a lot of what's called sustained G's. Either way, that G, the NZ, can go up at any velocity and stall the airplane. So yeah, when you ask them what the stall speed of an airplane is, it's kind of a meaningless number that a pilot would give you, right? Because the stall speed the airplane doesn't depend on airspeed for its stall. It only depends on angle of attack. So what's implied when the pilot says my airplane stalls at 55 miles an hour or 60 knots, what's implied? I'm at 1G. He's implying that you're in equilibrium level flight. And if I get to 55 miles an hour, my angle of attack is 16 degrees and the airplane will stall. Will that airplane stall at 16 degrees if he's going 100 miles an hour? Absolutely. Absolutely. If he pulls hard, he will stall the airplane at 100 miles an hour. And this equation will show us how that happens. That's called maneuvering flight. So you have to be careful when you're maneuvering flight, because between 1G and the maximum G's on an airplane, a small airplane has maximum G's around 4. So you can actually stall the airplane at any speed from 1 to 4, from 1 to 4 G's. And here's the kicker: the stall in a high G, a maneuvering stall, is almost guaranteed to spin entry. It's very dangerous. Kills a lot of glider pilots. Glider pilots think they know everything about stalls. They start doing high G stalls in a glider. Next thing they know, they're in the ground. Very, very dangerous. They have a high G maneuver, but you can do it. So if you're hearing stall speed from someone, what are they saying? That's a 1G stall speed. You can have 0 G's. I just make this a dart, right? I'm flying. How's it go? And the airplane's generating no lift, so the airplane's just falling. So if you were released in the cockpit, you would just be floating free, right? You could do that in an airplane. They could do that for the space people that just came on. That's called 0 G. You're not pulling any lift. At 1G, lift equals weight, and you're pulling your aircraft weight, equilibrium flight. At maximum G's, that's the maximum lift you can put on the airplane without bending or breaking the wing. So how would I break the airplane? How can I break this airplane? Well, there's an airspeed that allows me to pull maximum G's. That's called maneuvering speed. At maneuvering speed, typically it's 3 times the 1G stall speed. At 3 times the 1G stall speed, I can pull around 9 G's. Right? If this airplane is a 7G airplane, and I'm at 3 times the stall airspeed, I can pull 9 G's on that airplane. What's going to happen? Break the airplane, right? I'll break the airplane. I have to test my parachute to see if it's working, because that's what you're going to do. So the maneuvering speed is an important speed. The maneuvering speed is the fastest you can go, and you can yank back on the stick as hard as you want, and the airplane will pull max G's and stall all at the same time. Right? It won't let you pull more than max G's because it's going to stall right there at 3 times the 1G stall speed. So, does that make sense? If you go faster than that, and you can, certainly in the dive, I can go faster than 3 times my stall speed. All airplanes fly that. Airliners fly faster than 3 times your stall speed. That means they can pull more than 9 G's. So you could pull, yes, you could pull the wings off in airliners, right? Easily, because you're past what's called maneuvering speed. And pilots, even fighter pilots, don't like to go that fast unless they're escaping something. So the Navy calls it corner velocity because Navy changes the name of everything. Navy doesn't have pilots; they got aviators, right? And so they don't have maneuvering speed. The Navy has corner speed, but it's the same thing. Maneuvering speed and corner speed is the max. Usually it's around 3 times your stall speed, and it's as fast as you can go and pull around 9 G's. If your airplane's a 9G airplane, go faster than that, and you could break your airplane. Has that ever happened? Yeah, I pulled 10 G's in this once to avoid a mid-air collision. I had a student in the front seat. I thought he was going to hit the guy ahead of us on a rejoin. So I pulled, and he was pulling at the same time. We bent the wings. It didn't hurt us, but we did bend the wings a little bit. They had to fix it. Fortunately, they did not send me a bill, but I did get in trouble with the wing operations officer. That was at Edwards. So above maneuvering speed, the airplane will. Let's see, let me get my good spotlight back. Above maneuvering speed, pilot can break the wings. Below maneuvering speed, the aircraft will stall first at any velocity that he pulls maximum G's. So when you hear the stall speed from a pilot, what's he telling you? 1G. He's telling you his 1G stall speed, right? A lot of pilots aren't taught it correctly, and they don't realize that they can stall if they think if they're doing 80 miles an hour in an airplane that flies at 55 stall speed, that they're safe. They are not safe. They could stall in the turn to final approach. If they turn to final approach at 85 or 90 miles an hour and pull hard enough, it will stall the airplane and enter a spin. Kills people every year. I don't know when the FAA is going to change how they train pilots to get that across. But you have to be very careful pulling G's in the traffic pattern because, because a lot of pilots, especially new pilots, think that I'm above the stall speed, so I'm going to fine. No, you're not. You're not fine. You can stall at any airspeed. That's called an accelerated stall. And this is a little video of how it works. So what we got here is we've got this airplane and he's in a fast descent. He's above stall speed and he pulls up rapidly. He pulls up too hard. So he's coming down, he's coming in and he pulls up rapidly and he gets the max angle of attack and he stalls. Then he goes down again, but this time he recovers more slowly, and he gets the slide. That's called an accelerated stall. Let's see if I can get to show you what it's like.
So let's take a look at an accelerated stall above your VSO stall speed.
Starting out, the airplane was going fast, and inertia was holding it on its path. The G-force that the airplane felt was the result of the elevator trying to pull the airplane off that path. As the pilot pulled harder and harder on the yoke, the G load increased. To carry the extra load from the G forces, the wings had to generate more lift, which meant that the angle of attack had to increase. But because of the starting speed and the fact that the airplane was in a dive, the airspeed stayed high. As the angle of attack increased, the direction that the aircraft was actually traveling started to diverge from the direction the nose was pointed,
That's the stability
like a
axis.
sitting car. Finally, the pilot pulled the yoke back even further, and boom, the wing reached the critical angle of attack a long way above 1G stalling speed. We call this an accelerated stall. Even though the airspeed was high, the wing simply could not produce enough lift to carry all the extra weight from the increased G loads. Or, to revisit our engine metaphor from earlier, the wing had plenty of fuel to work with, but it wasn't being delivered in a usable form.
Gotta be careful with those metaphors. I love using them, but I don't know, sometimes they can really get you in trouble. So that's called an accelerated stall. It's very dangerous, and it kills pilots pretty much every year. And what it means is that you are between 1G and G max. You're between 1G stall speed and maneuvering speed. That's where you can have a accelerated stall. And usually the motions after an accelerated stall are very violent, can be very dangerous and violent in the airplane. And a glider. Now, once you're past maneuvering speed, you're not safe. You can't stall anymore. You'll pull the wings out, right? You'll pull the wings out. So, hey, I didn't stall. Well, yeah, okay, you got to start. Good luck with that. Okay, so these are the equations that we've got, and what I've kind of done over here is, I've kind of taken the L over SW, and we've called that upward pressure, right? And we divided that by dynamic pressure. So it's upward pressure over dynamic pressure. Right? And now you know why that's not drag. Hopefully you know why that is not drag. And then lift I can replace with the normal acceleration times the weight. So I can end up with NW over SW, right? That's again the upward pressure divided by dynamic pressure. And then I know dynamic pressure is equal to NZW over SW. If I can replace the dynamic pressure with 1/2 density times true airspeed squared. Or I could replace that with 1/2 the sea level density times V equivalent squared. So these two are two different ways of expressing Q. There's two different, you can express it in terms of sea level. That gives you what's called equivalent velocity or pressure velocity. That's what your PILO system measures in an airplane. It measures equivalent velocity, indicated velocity. There are different words they use, but for our purposes, we just use equivalent. But you can see how complicated this, I don't know, is it that complicated? Let me see. Not sure.
Well, good grief, what are you doing? Do you expect students to learn how an airplane flies looking at those equations?
Yeah.
Really?
What are you? Who are you?
Well, I'm your younger self. And that's probably why you have wearing that mask, so people can't see just how ridiculously old you are.
No, I'm not worried because I'm old. It's a COVID thing. It's a COVID.
Right. I heard yesterday a young woman in the class came in and asked you or told you that you taught her father here at Cal Poly.
Well, maybe she was mistaken. She could have been mistaken,
Yeah, mistaken, sure. If she's mistaken, it's probably because it was her grandfather. All right, well, good luck with that.
Acting problem. Quit playing with this stuff. I'll get it under control. We'll be okay. All right. So to review, the lift curve slope and angle attack are pretty much, they're in different units, but they're related by function that have pretty much the same slope. And let's see. wing shape, right? So this is kind of a view graph of things that I think are important. Now, if I put that view graph on as the first view graph, then I wouldn't have to worry about class size anymore because you all have to use the gone. But now hopefully you can work your way through that equation and see how a simple equation gives you tremendous insight, right? The first variation gave us lift pressure over dynamic pressure. Isn't that cool? That's what makes sailboats go faster than the wind speed, right? That's what makes an airplane fly. It's just lift pressure is bigger than the dynamic pressure. That's amazing. There's nothing to do with drag right now. Of course, in a boat, your drag comes from being in the water. That's why you can go faster, because if you have a pencil-shaped boat or something that's up out of the water, there's no drag. You can go 100 miles an hour in a 20, 30-mile-an-hour wind in a sailboat. So that's what that first variation shows you. Then we have the variation that we substituted Q. The density, of course, decreases with altitude. And I'll kind of stick with English units in the class. Otherwise, you could use the toolbox that I showed you. And here's the G's. Well, then we bring the G's in at 1G. Now, if I have 1G at maximum lift, if I'm at maximum lift at 1G, if I'm at maximum lift at 1G, I get the 1G stall speed. The angle that gives me that's the pilot's quote as their stall speed. If I'm going faster than stall speed, suppose I'm going twice as fast as stall speed. Well, if I'm going twice as fast as stall speed, how does that affect this equation? Well, look over here. If I put 2 VTAS in here, if I put a 2 in there, twice stall speed, let's go over here. If I put twice stall speed in here, what happens when that 2 gets out? It's squared, right? It goes to 4. It goes to 4. So that 4 is going to end up that means I can pull 4 Gs, right? The CL max equation will still be balanced. If I put twice the speed in here, it comes out as a 4. That 4 will end up in the numerator, and CL max will then allow me to pull at twice the stall speed. I can pull 4 Gs. What if I put a 3 in there? 3 times the stall speed. Well, 3 will come out as 9. That 9 will end up in the numerator. That means I can pull 9 Gs at the same CL max. Notice what stays the same. No matter what my G load is, CL max is always CL max. Angle of attack max always. That's why stall does not depend on your velocity, even though most pilots use it the 1G stall speed. So the shape determines how CL looks like. The shape determines it. Slats change the camber, and spoilers change the drag. The spoilers were those things, again, this airplane doesn't have them, but if they had them, it would be flaps that would just come up and like a glider has to slow the airplane down. On the parts of the airplane we talked about were aileron, rudder, elevator, horizontal stabilizer, vertical stabilizer, flaps, slats, speed brakes, and aircraft trim. And we saw that there's at least three ways to get trim. For a tiny small airplane, you're going to have a trim tab, a tiny tab on the back. Right? A bigger airplane like this is going to have electric trim. And that electric trim is going to move the whole stabilizer. Then you have a fighter aircraft, which trim just is done with springs and a force field system that alleviates the force in the cockpit. Different types of trim. So let's go over what I would expect you to be tested on today. Be given these equations on the right. Those are the formulas that are available on Canvas. How does the relative wind and the chord line of the wing contribute to aircraft flight? Hopefully you know how to answer that question today. Or the other way to answer that question is, how does an airplane fly? If an airplane doubles its airspeed in level flight, what happens to the coefficient of lift? Well, again, we'll go over this equation. We'll go over this equation right here. If I double my airspeed, what happens to Q? Q goes up by a factor of 4, right? If I double my airspeed, Q goes up by a factor of 4. That 4 is then going to what? It's going to reduce C sub L by a factor of 4. So if C sub L was 1, and I double my speed, it's going to go down to 2.5. Yeah. Okay, that will increase next week. So you see, the equation tells you and gives you an enormous amount of information on practically on how an airplane flies. What happens to the magnitude of the angle of attack if I double my airspeed in level flight? Well, the angle of attack is going to follow C sub L. If C sub L goes down by a factor of 4, the angle of attack is going to go down by a factor of 4. If the angle of attack was 8, factor of 4 would now the angle of attack would be 2. Does that work? So if you're following me, you did good today. Right? You did good. You knew more than a lot of pilots actually did. You know more than I did when I was learning how to fly. I didn't pick this a lot of the stuff up until I was a test pilot. What happens to wing loading and angle of attack if an aircraft in level flight picks up a lot of icing? We'll talk about this next week a little bit. So if I'm flying and I'm getting icing, what's happening to my airplane? What would you think is the first thing that happens? I start picking up icing. It's heavy, right? So it's just like I was adding fuel to the airplane. I get heavier and heavier. So if I'm in level flight and the airplane's getting heavier and heavier, what do I have to do to keep it flying? If the weight keeps increasing, I have to keep increasing angle of attack. So what's going to happen when I pick up enough ice to get to my stall angle of attack? The ice will fall off and I'll be safe. No, no, that's not. I'll stall, and after I stall, the ice might break off and I could recover. But most people die. So, so we're going to look at an accident next week. We're going to look at an accident that we just totally preventable that changed the aircraft industry, changed the whole aircraft. It happened in 2009. I'm pretty sure you're not aware of it, but it changed. It was transitional. I call it a transitional accident. Everything changes when it happens, and 9/11 is an obvious case, right? But this happened in 2009. It's only known within the aviation community. It was basically caused by icing. We'll talk about that next week. Another transitional accident that changed the airspace, and we don't know how it's changing yet. Is well, there's two, right? There's the MAX accidents that changed airspace aviation totally, and now you got COVID, right? You got the virus. People fighting on the airplanes because of the mask. So everything is in flux and everything is being changed, but we're going to focus on the things that get the most change.
I'm wondering about the variable surface area of the wing. Is that the surface area of the wing perpendicular to the travel of the air?
Yeah, the wing, the SW here is this wing. Yeah.
So that never changes. That's just
it changes if I increase this. No, you're basically it never changes.
Okay.
Yeah, fundamentally, it never changes. Yeah, it would change by a third decimal point out there.
Okay.
It would change. Yeah. Now the drag area is this area. That area. It's not this area. So the drag, if I'm using the area for drag, it's this area. Or it's you hold your hand out the window of the car. Yeah, go
So,
ahead.
yeah, that answers my question. The analogy of the hand out the window would pertain to the front.
Yeah, the hand out the window is Q. It's Q whether I'm doing this or whether I'm doing this. It's Q. Well, what's drag? Drag is if I could look at a picture of what's happening to the air. When I went like this to this, I see turbulence back there. I see turbulence, and my hand would be pulled back because I went like this. Not because of the Q, it would be because of that's induced drag. That's what's missing from that part. Okay, so what happens to the stall if the flaps are lowered? What happens to the magnitude of AOA if the slats are extended? Okay, well, we get pictures. I showed you pictures of that. Right, we should be able to do that. Here's the quiz. I move that? No, I can't move it. Dang. How come I can't move? Okay, well, here's after the quiz. So there's some more things. Here's like question 13. Let's just look at it. If an aircraft maintaining level flight doubles its true, this is where I get dirty. I could cut the Zoom guys out now, right? They wouldn't get the answer. No, I'm not going to do it. If the aircraft maneuver maintains flight doubles its airspeed, the coefficient of AOA and lift. We just did that. Well, where's that guy now? Well, what would happen? They'll both decrease by a factor of 4, right? We just did that. We doubled the airspeed. Airspeed came out of Q as 4. The 4 is in the denominator, so it's going to decrease the CO max and angle of attack by a factor of 4. Aircraft in level flight is picking up a lot of ice. What happens then? Denzel flying? That's my first question. The wing loading definitely will decrease. Well, that's wrong, right? If you're picking up weight, if I'm picking up weight, and this is wing loading, how is that going to decrease the numerator? The dynamic pressure will increase from the ice buildup. Yeah, dynamic pressure has nothing to do with the ice buildup. Has nothing. If I spam call, maybe I should take it. The dynamic pressure has nothing to do with ice, right? The dynamic pressure comes from a tube. You see, here's the tube right there. It comes from a tube at the end of the airplane. Now it can ice over. What happens to the airspeed if it ices over? It's to zero, right? Because it's not seeing any pressure. That's this airspeed that is this guy. That's the pressure airspeed that you're seeing in the cockpit. So that's the only thing I have is ice. So that's the second answer. The wing loading definitely will increase. And AOA may approach stall value. That looks good. That looks like a winner. Let's take the next one. Aircraft weight will increase, but wing loading will stay count. You know that's wrong right there. The wing heat generated from normal flight dynamic pressure melts any ice from weather and thus has no effect on aircraft flight. Well, that is wrong. That is definitely wrong. You can ice almost any time. You get to cold, humid air, you can ice up, even with temperatures above 32 degrees. A cambered wing stall and level flight at 16 degrees. I'm at 200 knots at 4 degrees angle of attack. What airspeed will the wing stall if it slows down? Okay. So I'm at 200 knots at 4 degrees and it stalls at 16 degrees. So what airspeed if it slows down? Well, I don't have the coefficient lift, so I'm tempted to look at this one, right? Unless I had this class. So what's the factor of that AOA changes? What factor is it? The factor of 4, isn't it? So if AOA changes by a factor of 4, what factor does C sub L change? Factor of 4. So if I get a C sub L factor of 4 change, what has to happen to the velocity over here in Q? It's the double. That's the double. So it must be 100 knots. If it's 4 degrees at 200 knots, if I slow to 100 knots, if I slow to 100, the AOA will go up by a factor of 4 to 16. So it must be 100 knots. You see how it worked out? You see how important the equation is? Yeah, and you see the difference between math that works and math that's just a bunch of numbers, right? And that's what I'm trying to get across. These equations are important. They really important. And they dealt with things that are critical to kill people if you don't get it right. What effect is lowering the slats having? All right, I'm not going to tell you. You guys know. Oh, guess that's it. I'm done. All right, join the group, everybody, if you can. Have a good weekend. Don't forget your group number. Don't forget your group number. Okay, guys, thank you.
Thank you.
Hey, thank you. All right, everybody, guys, resuming.